Hello, everyone. This is my physics lab report for Physics 2211, Lab 4, Oscillations. My name is Yuvraj Deval, and let's get started. All right, so in introduction, so the fundamental principles we will be observing in this lab is Newton's second law and the energy principle. Newton's second law is F net is equal to the change in momentum divided by the change in time. And so in this situation, our net force is equal to the force of the spring plus the force of gravity, or that F net is equal to Ks plus mg. We are also using the energy principle, and the energy principle states that the change in energy of the system is equal to the work done by the surroundings. In this case, we are choosing our system to be the mass, the object, and the spring, and the earth. And our surroundings we've chosen to be nothing. So because we've got nothing in our surroundings, that means no work can be done on the object by the surroundings, on the system by the surroundings. So thus, we can state our equation to be the change in kinetic energy plus the change in gravitational potential energy plus the change in spring potential energy to be equal to 0. All right, so what is the purpose of this lab? Why are we doing this? So the purpose of this lab is to observe and measure the motion of a mass swinging in an arc while oscillating on a spring. And so the motion will be analyzed using Tracker, and we will model it out on Python using Python on GlowScript. And so what's the goal? Our goal is to determine if this model that we've created in Python satisfies the energy principle. And so a little bit of a preview or the result of this lab is that the total change in energy of the system remains equal to 0, meaning that the energy principle is satisfied as per our last slide. All right, so some initial conditions. The mass of our object is 0.402 kilograms. This is determined from the pre-lecture video of the lab. And our initial position is negative 0.11, negative 0.634 meters. And this is found from Tracker. And our initial velocity is 0 meters per second because our object is being released from rest. And our spring constant is 7.486 newtons per meter. Our initial spring length is 0.7 meters, and our rest spring length is 0.174 meters. And so these three, initial spring length is given in the video, and the spring constant and rest spring length are both calculated through the two little formulas on the bottom of the screen. All right, so some code. So our initial conditions we set here are mass of our ball, the ball position, the ball velocity. We've got our t, our time t, and our delta t. We've also got the gravitational constant, the spring force constant, and the initial length, the rest length of the spring. We've also calculated L hat, and S, which is the difference between L and the initial length. And we've also calculated the initials, the initial kinetic energy, the initial gravitational energy, the initial spring potential energy, and we've calculated the initial total energy. And so these will be used in our loop in the following slide. So in our loop, we're calculating our force of gravity, the force of a spring, and we're calculating the net force. And from the net force, we are calculating the velocity and the position, using the position and update velocity formulas. And then afterwards, since our position has changed, we've got to update our spring force. And so that's what this final 3 lines of code is on the left image. We are also calculating the change in energies. So this is done here. We can see we've got our delta K, delta UG, and delta US, and our delta E. All right, so to the meat of the conversation. What is the differences in our observers and computations for the motion? As you guys can see, we've got our model does a pretty good job of representing the actual motion. However, there are some differences, and this can be attributed to the fact that our experiment is not a closed experiment. This means that there are other forces besides our spring force, besides the gravitational force, that are affecting our system. So while our model may not be perfect, it is pretty accurate. All right, so back to the main question of this lab. Does this motion satisfy the energy principle? And the answer is yes, because the definition of the energy principle is that the change in energy must be equal to the work done by the surroundings. However, in this case, since we chose the surroundings to be nothing, we expect there to be no change in energy because the work done by the surroundings is 0, and which is shown by the graphs because the orange line is a constant and it's equal to 0, and the orange line is delta E. All right, so the final question is the X and Y oscillations. So to calculate oscillations, what we did was I calculated the time of 3 periods divided by 3 to get a more accurate length for the period, and then I calculated the K constant. As you can see, the K constant is different for the X and Y directions because the oscillation, they have separate periods for both oscillations. So this can lead to drastically different numbers for our model, and so it's important to figure out which direction you are using to calculate your K constant. All right, that's the end of this slideshow. Thank you all for coming for lab 4. I'll see you guys at the next lab. Thank you and goodbye.